and T is del T. These ones form the underlying vector fields for the group Hn. So with this, we have the computational relations for this group, xj, yj, equal to 4 delta ij t. This is the computational relation. And every other one, xjt equal to yjt equal to xij equal to all that 0. So with these vector fields, we could discuss also what we call the Heisenberg Laplacian. This is just like the usual normal Laplacian, which you write as C del squared del x. Okay? Del x squared. Okay? J equal to what? Equal to 0. So this is what we call the Heisenberg Laplacian with respect to the vector fields, underlying vector fields of this Lie group. So with this, it means that we can even express this as, okay, in the real form, like this, to obtain this, which we now call this. This is the Heisenberg Laplacian, and this is sum del squared del xj plus del squared del yj plus 4xj del squared del y del t minus 4yj del squared del y del t del x del t plus 4xj squared yj squared del squared del t squared. This is the real Heisenberg Laplacian. Now, our aim is, if you have this kind of Laplacian, how do you solve it? Solving it like usual PDE works when you don't have all these things like you do the other one. So, in most of our works, what we try to do is to solve this by factorization. So, you try to factor this whole thing into an operator which is into one here, and then another one which is also this. But we find that after the factorization of these operators, you find that A dagger will not be equal to A dagger T, A dagger A. So it means that you will also get a computation relation of this form, such that you will have A dagger will be equal to some 2 delta ij t. So after we have solved it, we have factorized this, what do we now want to do with it? The aim is to have a solution for this. If you solve it classically, you find that all the solutions are trivial. So because the solutions are trivial, we now seek a group invariant solution using symmetries, and then we get some. With this, we can now generate what we call spherical functions. So we have the solutions that we get will be like exponential functions, which satisfy spherical functions, and with that we can do group algebras of these spherical functions. And so these group algebras are what leads us to the concept of Levant pairs. In fact, if you have the group, say H, there is what we call dilation on this group. say UT, what happens is that this dilation gives you lambda U, lambda squared U. And so these dilations form a kind of automorphism on the group. And so we can discuss group of automorphisms. And the action by the automorphism, if you pick any element on this, say, sigma, and then you can get an action of this, so that if you have UT as element of Hn, and there's an action, it gives you just UT. With this, we can now look at, say, you have H, then a subgroup of automorphism K, a pair. You can say these two is a given pair if the algebra of H, okay, H.
Change your marker.
Yeah, sorry, K, H. This is called the continuous linear functions on the double coset.
You can see. Change your marker.
Okay, sorry. Okay, yes. Okay, so we have the space of continuous functions on the double coset where K is a group of automorphism of Hn. So you can actually pick an F here. This F satisfies K, U, K equal to F of U. If it satisfies, okay, I will just make statements about it. Now, if we have this set of functions, we have a lot of things that we do on them. We can do distributions on this space, provided they have compact supports. We can generate some exponential functions that do not change their status. We can generate a lot of things. So on this group, there are a lot of things. They have applications in quantum mechanics. They have applications in representation theory. They have applications in cohomology. In fact, I'm trying to solve cohomological equations on this group now. And so, with the cohomological equation I'm solving right now, I'm doing it on the discrete Heisenberg group. The discrete Heisenberg group is realized as an upper diagonal matrix of this form, which also has its own Lie algebras in that form, with 1, 0, 0, 1 and all that. So I'm trying now to solve a cohomological equation of this form, F composed, say, gamma, equal to, say, G, where this is a diffeomorphism of it. I've just concluded that now. So I think I have said something. There are a lot of things to talk about. Maybe. So, Prof.
Operators arising from there.
I said so. There's no commutative.
No, not commuting
Operators. Yes.
You generalize that.
In fact, the operators are non-commutative because these ones are composition of operators. These ones are first order differential operators.
What I am saying is that from this discussion,
Yes.
general theory of non-commuting operators.
Yes.
As a field.
So we welcome students to come and
Yes.
share with us.
So that invariance
Yeah.
expression,
This?
yeah.
Yeah.
Don't you need the inverse of one of the cases?
No, not necessarily. Not necessarily. If we do that, then we are back to left regular representation. You can still have.
If one of them is
Yes.
inverted.
Yes.
Okay.
This is the way it behaves. That's why we call it double coset. It behaves just like that.
From there,
Yes.
can we also represent the discrete in terms of the Kalinski spaces?
Yeah, I've said that if what I'm doing now is trying to solve cohomological equations on the discrete Heisenberg.
What I'm saying.
Yes.
What is?
Okay, using the Kalinski spaces on Z.
Yes.
No, I'm not doing that. Yes.
I'm just curious. In physics, when we talk of non-commutativity, usually we have that brings up uncertainty relations
Yes.
between
Yes.
the dynamical variables. And this Heisenberg case is actually a specific case.
Yes.
When we are talking of position and momentum.
This exactly.
Yeah. So I'm now wondering whether you also considered, I don't expect it actually, but I'm wondering whether you did consider uncertainty.
All these things I'm doing are uncertainty principles.
Really?
All of them. They are from uncertainty principles. The only thing now is that we are bringing functional analysis to it. And that is why it does. It's exact. All the examples are from physics.
In fact, that's why you said
It's
non-commutative.
See, that is just the fact. They are all Heisenberg uncertainty principles. That is the foundation of it. If you are doing the representations, you find that it's position and momentum operators that we use for the generic forms of the representations. Yes. So, and then the space that we work on for the representation are the phase space. So,
thank you very much for that question. The answer, I think, very
Yes.
specifically narrows to something that's
Yes.
Can I just ask a question, please? What are the Casimir invariants of the Heisenberg?
you mean in terms of operators?
Yes.
And the only difference is that for Casimir operators, if you solve them, you get what we call Hermite functions. They are all orthogonal polynomials, but not all of them satisfy these double coset properties. Not all of them. What brings us to double coset property is semi-direct product of the Heisenberg group and its subgroup of automorphisms, and that is not in physics.
Actually, I'm
So, but the Casimir operator is also a type of Laplacian that when you solve it, what you have is either Hermite or Lagrange polynomials.
So, the Heisenberg Laplacian itself is a Casimir operator.
But it has.
The universal relative algebra of the Heisenberg group itself.
Well, actually, I was asking about the invariants of the question of the group. The variants.
Okay, different variants.
Invariants. Invariants.
Okay, invariants. I cannot say because I know that I have done some work on I have read a lot on Casimir operators. But my direction is not on that. What I needed was to see how I can use my PDEs, get a solution that will look like what I want. So I only deal with functions that behave in this sense, provided they have compatibility. And that is the functional analysis.
So, for example, the invariants of the quantary group are the spin.
Yes, the spin or U1. Yeah. So this K, a typical example is SU2 or SUN. You can take special unitary groups to do your K, or the unitary group itself, or even the torus. You can use them. But when you talk about spin, then you'll be going into like block matrices. In that sense. So,
Okay.